and to attend this meeting this interesting presentation with the suggestive title, You are not in the Witwatersrand anymore. Probably Daniel will be able to pronounce it better than me. And let me give you a few hints about the speaker, and I will give him all the board to do whatever he thinks is best. So Dr. Daniel Britt is the Pegasus Professor of Astronomy and Planetary Science at the Department of Physics from the University of Florida, the Central Florida University. He was educated in the University of Washington and Brown University. His Ph.D. in Geological Sciences from Brown in 1991. He has a varied career, including service in the U.S. Air Force and in the ICBM missile launch officer and an economist for Boeing. A lot of things. He has served on the science teams of 4 NASA missions, Mars Pathfinder and Deep Space One, the New Horizons, and Lucy. He was the project manager for the camera on Mars Pathfinder and has built hardware for the NASA Mars lander. As you can see, everything is impressive. He currently does research on the physical properties and mineralogy of asteroids, comets, the Moon, Mars, and several NASA grants. Is the director of the Center for Lunar and Asteroid Surface Science class, or at least in Spanish, something like that, which is a node of NASA, Solar System Exploration Research Virtual Institute. He was served as the chair of the Division for Planetary Science of the American Astronomical Society and the Planetary Geology Division of the Geological Society of America. He has a lot of honors. To be a Pegasus professor is one of them, but also these honors include 7 NASA Achievement Awards, election as a fellow of the Meteoritical Society, and an asteroid named after him. It's the 4,395 Dan Britt asteroids, which is something that I really buy. Okay, so thank you very much, Dan, to be here. For us, it's a real honor. We are really happy to have you here, and you can begin whenever you want. I will shut down my camera and my micro to let you have all the control of the presentation. But everybody will be here. If you need us, you only need to ask. Okay.
Okay. So, well, thank you very much, and thank you for the introduction and the invitation. It's great to be here. This is not a huge group, so if you have questions while I'm talking, of course, go ahead and ask them, or you can ask them in the chat if I can figure out how to run the chat, of course. And I'll certainly be willing to take questions afterwards. But I throw out this provocative title, you're not in the Witwatersrand anymore. The Witwatersrand, of course, is a classic ore and geology province in South Africa, which is one of the richest ore deposits in the world. But it's a terrestrial ore deposit. And I'll show you what that means. But fundamentally, the geology of extraterrestrial objects is different from terrestrial geology. You've got to think about planets not as just solid bodies, but as huge physics, chemistry, and biology experiments. And what happens is that the chemistry, the available energy, the heat, the gravity, all of these things combine to produce much different geological results. And they have a fundamental impact on the economics of potential resources. One of the things that most people don't realize is that minerals evolve and they diversify. And this is just in reaction to changing chemical conditions.
Dan, sorry for the interruption, Dan. Seems that somebody did something and we are not able to see your presentation anymore.
Oh,
Can
okay.
you try to share it again.
All right. Yes. How's that?
Now it's okay. Thank you very much. I'm sorry for the interruption.
Not a problem. So, as I was saying, mineral assemblages evolve and diversify. So in reaction to the unique chemistry on Earth, the Earth has about 4,600 different minerals. Asteroids have less than 250. The Moon has about 350. Because basically its mineral evolution was shut off at a much earlier period. Now, that doesn't mean there's not economic value. It's just that the geologic rules are different. And the order of magnitude difference in the available mineralogy is just an indication of how different the geologic rules are. Bob Hazen wrote a whole series of papers on mineral evolution and basically identified 10 general stages. The Moon is basically stuck at stage 3. And it just doesn't go very far beyond that. I'm trying to get my highlighter going here. This is what you get with the Moon. Now, I'm going to make a little aside into economic geology, and one of the characteristics of this talk is we're going to cover a lot of ground. So I will be hopping around to different topics all the time. First topic is, what is an ore? An ore is not a geologic concept, it's an economic concept. It's a naturally occurring material from which a mineral or minerals of economic value can be extracted at a profit. And so this is an economic concept to begin with. And in terrestrial geology, ore usually implies or requires some concentration mechanism to increase the amount of the material available. Because what ores typically are, like this guy is pointing out, they're small concentrations of material surrounded by vast quantities of uneconomic rock. In lunar geology, the concentration mechanisms are very different than terrestrial concentration mechanisms. Quite often they're non-existent. Now, example of terrestrial concentration is platinum. The average crustal abundance of platinum is 5 parts per trillion. The major resource for platinum in the world is called the Marinsky Reef, which is in the Witwatersrand. Its abundance is about 10 parts per million. But that means that it's a factor of 2,000 concentration over crustal abundances. And you see the little black lines in this white rock. Those are the platinum ores. The Marinsky Reef and the world's resources of platinum are in a zone about this big vertically. It goes for hundreds of kilometers across the Witwatersrand. And that single feature contains 75% of the world's platinum. But it's that concentration that occurred in that zone that makes it economic. And concentration is really the key to economic geology. Most economic minerals are hugely concentrated. Here's a picture of a block of gold ore, about 860 kilos, and that's the amount of gold that can be extracted from it. And basically, you're talking about concentration factors in the hundreds or thousands for most common ore minerals. For something like chromium, concentration factors of 1,500. Lead, 2,500. Uranium, 500. And we'll learn more about that as we're going. But basically, what's happening on Earth is you have a disseminated source of these materials at low abundance. And you've got some process which liberates that, usually chemical interactions typically involving hot fluids, brines that are either strongly acid or strongly base. And then these brines move the resource-bearing fluids to a source rock and an ore body. And then you trap these things in some geological feature, quite often faulting. And that produces things like veins. The result is usually highly localized deposits of highly concentrated ores. This typically requires fluids, heat, high pressure, and lots of time. And so, really, the whole point of terrestrial economic geology is to narrow down your knowledge, essentially localize the resource with finer and finer knowledge of the site. Because what you don't want to do is you don't want to move a lot of uneconomic rock that doesn't have ore. And so you try to minimize your costs by maximizing your knowledge of the site, because these resources are so discrete. And the distribution of ores is typically driven by plate tectonics. Now, the slide I'm showing is a distribution of copper deposits. And these things are associated with continental collision. In fact, you can basically map out the history of continental collision by just looking at the distribution of these ores. And it's continental collision that quite often provides the heat, the fluids, the pressure, and the fault trapping for mineralization. The thing with the moon is that all of that is irrelevant. There's no plate tectonics. There are no continental collisions. There's no extensive water. There are no hydrothermal systems active now. There's no active volcanism now. There's no mantle reworking. You're dealing with a much lower heat flow and much lower gravity. And remember that actually in terrestrial mining, gravity is a major resource, because a lot of terrestrial mining uses the pressure of gravity to excavate and to crush rock. And when you're on the moon, you're dealing with gravity at 16% of terrestrial. You have a much lower resource there. And of course, you have much less diversity in mineralogy. So there are resources, but the geologic and of course then the economic rules are going to be different. And you have to live by those different rules. Now, as I was saying before, you have to think of planets as this huge chemical and physical experiment. And really, the geologic processes I just talked about are only the last stage of whole planet processes that involve differentiation and concentration. What happened in the Earth is that the whole Earth melted, created an iron core, an olivine-rich mantle, and a lighter silicate crust. And so the abundance and chemical affinity of those materials during differentiation drive what resources are available. And at the very first stage of differentiation, you're actually concentrating some resources in the crust and some in the core. And it's these abundances after you differentiate that really drive important mineralogy and even biology. You know, there's a reason why you don't breathe fluorine and your bones aren't made of strontium, is fundamentally abundances. And what happens is that the crust concentrates the so-called lithophile elements, things like silicon, oxygen, aluminum, magnesium. And the core concentrates siderophile elements, iron-loving elements. And I want to just point out a couple of things. In the whole Earth, iron is very abundant, 35%. And magnesium is relatively abundant. But in the Earth's crust, iron is depleted by a factor of 6. Aluminum is enriched by a factor of 7. Oxygen is enriched. But potassium doesn't even make the list of whole Earth abundant elements. But you see it's hugely enriched in the crust. Sodium also is hugely enriched in the crust. And it's these enrichments that you have to keep in mind. We basically look at chemical affinity by dividing elements up into lithophile, that is rock-loving, siderophile, iron-loving, chalcophile, ore-loving, and of course atmospheric elements, amphiphile. And so the lithophile elements tend to end up in the crust. Siderophile elements tend to be drawn to the mantle, to the core. And this differentiation produces a huge concentration or depletion in cosmic abundances. So things like potassium, which are actually not very abundant cosmically. The potassium is something like 300 times less abundant than silicon, for instance. Get hugely enriched in the crust. Things like uranium get hugely enriched. Things like tungsten and samarium, europium, get hugely enriched in the crust. And oddly enough, if you look at cosmic abundances, gold and mercury are about at the same level. Platinum is hugely depleted because it's a siderophile element. And so with platinum, as I said, its crustal abundance is about 5 parts per trillion. But its cosmic abundance is about 1.4 parts per million. So a huge depletion because of this differentiation. So the moon is basically a product of double differentiation. What happened is the best idea right now is that the moon was created by a giant impact of a Mars-sized body crunching into the already differentiated Earth. And so basically the moon ripped off the crust and some of the mantle of the early Earth. But it was an impact between two already differentiated planets. So you depleted the iron in the crust already. And it was mostly crust and mantle material that formed the moon. So you're starting highly depleted in siderophile elements. The volatiles that would have been available would have been vaporized by the high impact temperatures. And the accretional energy, when you recreated the moon, essentially melted the whole body and generated a magma ocean. And so moon was initially molten. It differentiated again, a third essentially differentiation. Created a core, which is iron rich. And as the magma ocean cooled, it slowly differentiated. Tidal dissipation probably slowed that cooling and made it much more prolonged. And so it created a denser olivine and pyroxene mantle with the olivine and pyroxene that's early crystallizing, sinking, and the relatively light material, anorthosite, basically a plagioclase rock, would be floating, since it's less dense, on this increasingly dense ocean. And so it produced a olivine and pyroxene cumulate mantle and this lightweight plagioclase-rich crust. These high degrees of crystallization concentrated what we call incompatible elements, and I'll talk about that more in a minute. But basically, at the base of these are elements that do not fit in the crystal structure of most of these minerals, and that becomes a very late crystallizing phase. Basically, residual melts that last for a very long time. And in the moon's case, you end up with a layer of incompatible elements, a so-called creep layer at the base of the crust. Creep stands for potassium, rare earth elements, and phosphorus. And that's a potential resource because it's been concentrated by this planet-wide geological mechanism. So, incompatible element. This is an element that is unsuitable in size or charge to fit into cation sites and minerals. And they typically, as I said, get concentrated in late-stage melts since they don't fit easily into most crystallizing minerals. And they come in a couple of flavors. But fundamentally, there are things like large ions, potassium, rubidium, cesium, strontium, barium, or things with large ionic valences, zirconium, nobelium, hafnium, the rare earths, thorium, uranium, tantalum. These are all economically useful minerals. And these are going to be concentrated at the base of the crust. And they've actually been exposed by basin-forming impacts and late-stage volcanism. You can see in this image, this is the thorium content. And so this whole Procalarum basin is highly enriched in thorium and is probably enriched in rare earths, uranium, tantalum. And you probably have a factor of 300 or 400 in concentration in this element, and probably similar concentrations in other things like uranium. So what's happening here is this terrain is essentially a result of Mare volcanism that tapped the creep source regions. Basically, you're looking at a large proportion of the radioactive elements that are available on the moon, things like potassium, thorium, uranium. And these materials were incorporated into basalts that erupted out into the Procalarum basin. Now, I'm going to make a little transition here, but it's useful to remember that lunar basalts are much different from terrestrial basalts. This is just a chart of terrestrial basalts. Terrestrial basalts, mid-ocean ridge basalts, ocean island basalts, terrestrial basalts, and then lunar mare basalts. And basically, lunar mare basalts, at the simplest level, come in two versions: high titanium and low titanium. But high titanium is quite a resource of titanium, 10 or 11 weight percent. But they're also substantially more iron-rich than what you see in terrestrial basalts. Another thing to remember, though, is that that's only a very small portion of the surface area of the moon. It turns out that, of course, basically all the Mare basalts are pointing towards the Earth. 85% of the surface of the moon is the anorthositic highlands. And those are very iron poor, but very aluminum rich. And so you have to keep that in mind, that that's a resource in the lunar highlands is things like aluminum and calcium, not iron. So how do we know that? Well, we have a substantial collection of lunar samples. Apollo went there, they kicked around on the surface, they returned 382 kilograms of samples. We have some small sample, we have about 300 grams from the Russian Luna program. The more recent Chang'e 5 brought back 1.7 kilos. But remember that we have lunar meteorites falling out of the sky all the time. We've identified about 400 lunar meteorites, mounting to about 200 kilos of sample. And so you can actually see these were returned by Apollo at great cost and very skillfully. But little do we know that sitting out in Antarctica or in the deserts of Northwest Africa are other lunar samples that sample a much more extensive zone of the moon. So we have a lot of information to do a little economic geology. And most of the economic geology that we talk about is a regolith. This comes from the Greek regos, blanket, and lithos, stone, which is the mantle of fragmental and unconsolidated rock overlying bedrock. Now, terrestrial soils are a mixture of unconsolidated shattered rock material with organic material. Soils are fundamentally different from regolith. What you get on the moon is crushed rock. And what you see on the surface, almost everywhere, is this crushed rock regolith. It has no organic material. If you look at the stratigraphy, again, thanks to Apollo, we understand this pretty well. And the Regulus Layer is typically a 20 centimeter or so, very fluffy layer of loose material, very fine particles. And below the fluffy stuff, soil becomes much more compact. And it progressively gets more compact with depth. And the depth of the regolith varies with the age of the surface. On the moon, the Mare has about 4.5, 5 meters of regolith. The highlands, about 10 meters. So let's talk resources. In the near surface, you basically have silicates and water. Like all silicates, lunar regolith is roughly 40 to 45% oxygen. I tell my astronomy students this, and they're quite amazed that you can drop a rock on your foot, and half of its weight is just oxygen, air. That's just the way rocks are. The Mare has significant iron and titanium as a resource. The highlands are poor in iron, but rich in aluminum. The most accessible water is in the polar permanently shadowed regions. I'll talk a little bit about that, but the amount and distribution are actually unknown. And remember, the fundamental dominant surface process on the moon is impacts. And so regolith gardening is going to be going on for the age of the solar system. And it's going to mix the stratigraphy and distribution of any ice that accumulates in these polar permanently shadowed regions. These are essentially cold traps. There's also modest water deposits associated with pyroclastic glasses in the Mare. These were discovered in Apollo 17. But just to show you what we're talking about in oxygen, this is the molecular weight. This is the molecular weight of this crystal structure, and this is the weight of the oxygen. So basically, the oxygen content of most of these fairly common rock-forming minerals is between 40 and 45%. The average Highlands is about 45%. Apollo 11 was about 42% oxygen. Mining oxygen is not trivial. What you have to do is you have to break up the crystal structure of the parent material. A rough measure of this is the Gibbs free energy of reaction. And if you look at Gibbs free energy, for instance, everybody's familiar with electrolysis of water. That's about 230. To do the same thing to olivine is an order of magnitude more energy. This is an indication of how tightly bound things are to in their atomic structure. And so the feldspar, which is the most common mineral on the surface of the moon, is double that of olivine. So very strongly bound stuff. People are interested in extracting oxygen from ilmenite, and simply because it's a lot easier to do than silicates. So if you're prospecting for minerals, remote sensing actually works pretty well for many lunar minerals. Iron and titanium can be characterized by remote sensing pretty well. This is an iron map, and again, the iron is largely restricted to, as you would expect, the Mare regions. Titanium, same story. Pretty much the Mare regions. Prospecting done. But remember that these are quite poor resources by terrestrial standards. Ore grade titanium on Earth is about 58% titanium dioxide. Iron on the moon is mostly, again, in silicates, which are tough to get out compared with where you find iron ores on Earth. And we, of course, have learned a lot from our 2,800 samples of the moon provided either by NASA, Russian Space Agency, or the Chinese Space Agency, or natural processes and meteorites. And I will point out that this is aluminum versus titanium. So the felspathic highlands are down here, with essentially no titanium and a whole lot of aluminum. One of the Apollos went to a highlands felspathic terrain, but oddly enough, Apollo 11 landed right in the middle of a high titanium area. And of course, Apollo 17 explored a very high titanium or very, very diverse titanium area. Most of the other places visited by Apollo were much lower titanium. The other resource to think about is the fact that the moon's crust is a product of double differentiation. This is concentrated incompatible elements in the lower crust and is the origin for things like the creep terrain. This is a thorium map of the moon, and you're getting areas that have 10 parts per million thorium in the lunar surface. these are concentrations. This is about a 300 time concentration over cosmic abundances. And this is just one indicator of a potential resource here. Rare earth elements for uranium, for all the other things that I listed as incompatible elements. They should be strongly enriched. By what factor, we don't know, in these terrains. But that's a resource to keep in mind in the more distant future. And of course, water. Water is concentrated in the cold traps of the permanently shadowed regions by the poles. These things have accumulated volatiles over the history of the solar system, probably mostly in the early history of the solar system during the late heavy bombardment, when a lot of outer solar system material worked its way into the inner solar system and impacted the moon and Earth. And so you've probably got a substantial resource. The neutron spectrometer data estimated about 3 billion metric tons of ice buried in the top portion of the regolith in these permanently shadowed regions. That sounds like a lot, but that might be a relatively small weight percentage of any excavated material. We don't know yet. The other resource in the polar regions is power. There's areas of continuous night, but there are also areas that are either totally or at least mostly illuminated during a lunar day-night cycle. So you can get fairly substantial power resources from these areas in terms of solar power. Now, remember that, again, impacts drive the surface processes of the moon. So any of the ice that was deposited was not deposited in a static environment. And you're getting major impacts that are mixing the stratigraphy and depositing new ejecta on top of what could be ice layers. So when we're looking for ice as a resource, you should expect to find a stratigraphy of ice-rich horizons, interspaced by very ice-poor deposits from nearby ejecta. And this will be a factor in all scales, so from the meters to the thousands of kilometers. And it's useful to remember that these craters that are the permanently shadowed regions are actually fairly deep phenomena. This is elevation relative to lunar mean. And you're talking about the ice layers being at the bottom of kilometers that are of craters that are several kilometers deep. And of course, then you've got this interlayered mixture of ejecta horizons, gardened regolith, and probably thoroughly mixed stuff. So what we know about ice is that there's probably ice, at least in patchy coverage, close to the surface. There's also at least a reasonable amount of ice in the subsurface. There do not appear to be thick, pure deposits of ice. But what we don't know is how thick the surface ice is, what the textures of the ice and the regolith are like, what the ice concentrations are like in the human scales, the 1 to 100 meter scales that you're mining on, and how the concentration of ice varies with depth. Or if the ice is ore filling or ice lenses. So there's lots of things we don't know. This is what we hope to find out with missions like Viper, which NASA is sending to the South Pole in the not so distant future. So to wrap up, thing to remember is that mineral evolution is fundamentally different on the moon. The Earth is a lot less involved. The moon is a lot less evolved. Mineral evolution ended at a much earlier stage than Earth. Earth has an order of magnitude more minerals than the moon because it's been this huge, long-lasting biological and geochemical experiment. The geological concentration mechanisms that we depend upon for ores on the Earth do not exist on the moon. No fluids, no hydrothermal systems. What you get are oxygen and metals that are locked in silicates and are not trivial to extract. You get water in the permanently shadowed regions in unknown amounts and forms. And you have Mare volcanism tapping these incompatible elements that are probably substantially enriched in useful minerals, although enriched in useful minerals still means parts per million. And of course, impacts and shocks are the major driver for most on the moon for most of solar system history. So whatever you have gets excavated, gardened, redistributed by impacts. And I want to thank you very much for your patience and listening.
No, we want to thank you, Dan, for this fantastic presentation and for all this information. It has been wonderful to hear you. And now, if you don't mind, we want to let the attendants to ask questions if they want. So what we should do is to raise the hand virtually in order to ask questions. I have a few of them, but I will wait until someone else asks. I have something in the chat, maybe. Yes, Joaquin, please go forward.
Hello, thank you for the very interesting talk. I would like to ask you if my conclusion from your point of view is correct. I see a lot of potential, a lot of resources if we want to put a lunar base in the hopefully near future, but I don't see my conclusion from your talk is I don't see an economic interest to going to the moon mining for example, the creep materials and taking them back to Earth. I'm correct?
You're correct. I think the major economic driver is the comparative advantage between using local resources locally. Remember that it's still enormously expensive to drag material off the surface of the Earth.
Yeah.
And that's the comparative advantage here. So the whole advantage of local resources is it makes building bases and building infrastructure a lot cheaper on the moon. That's the economic case. There's very little economic case for bringing it back to Earth. However, there's visionaries talk about economic cases for in-space manufacturing and in-space construction. Yeah. And that's way in the future.
Yeah.
To be granted. But that's really the part of this is that there's a whole constellation of technologies that need to be matured in order to reduce the risk and make it economically possible to exploit and extract and utilize any of these materials.
Yep. We need to push forward in this direction, is my opinion. Yeah.
And it's many small technologies. The issue, for instance, in getting oxygen out of regolith is that the technologies to do that are still in their infancy. In addition to that, you need technologies to clean up the water because the regolith is full of all sorts of trace nasty things like like mercury and potassium and sodium and things like that, that have funky reactions.
Yeah.
And you have to, and that's just two. There's probably 50 of these technologies that are actually interdependent. And the sooner we move forward in researching and bringing these things to useful levels of maturity, the faster we're going to have things like self-sustaining lunar bases.
Yeah, I agree. Thank you.
Sure.
So before giving the word to Javier, wait a second, because you have Joaquin raised a very interesting point. Dan, your colleague, Phil, in his presentation, he talked about time schedules because we asked him. He was thinking about in 5 years or something like that, we will have a lunar orbiter.
Yes.
He thought that maybe in 10 or so years there will be a permanent settlement in the moon. What do you think about that? Do you think that is possible?
It's certainly possible. The technologies that we're talking about are not that tough. It just requires that that the funding be provided to do the necessary development. NASA works on things called technology readiness levels, TRL.
Yeah.
And a low TRL, TRL1 is something scribbled on a soggy bar napkin. And TRL9 is something that's operating on another planet.
Yeah.
And most of the technologies that we need are at TRL 3 or 4. They still have a long way to go.
Yeah.
And the only, and it's not all that technically challenging. It's just that nobody works for free, particularly engineers.
Yeah. Tell me about it. Yeah. So Javier, do you want to ask something? Go forward, please.
Hello.
Yes.
First of all, thank you very much for your interesting talk. My question is that you talk about the creep in the lunar surface or incompatible elements. And I'm thinking if it is possible to the rare earth to appear in an asteroid surface, or it is geologically impossible.
In an asteroid service?
Yeah.
Well, the problem is that the moon has been subject to two events of differentiation.
Yeah.
So that's really highly concentrated, these incompatible elements. For most asteroids or any asteroid that has not been differentiated, you get cosmic abundances. And cosmic abundances are very low, highly disseminated materials. So for most asteroids, rare earth elements would be what you see in cosmic abundances, which would be in parts per million or parts per trillion.
Okay.
And actually, we're lucky in that for rare earth elements, they're lithophile. They end up in the crust, and so planetary differentiation concentrates those. And you'll only get concentrations of those kind of elements in differentiated asteroids.
Okay. Thank you very much.
Sure.
So regarding this, because I think I remember to read somewhere that some kind of elements very rare in Earth, like iridium, for example, are not as rare in asteroids, or at the very least, you can find an asteroid which is full of iridium or something like that.
Well, sure.
That...
Yeah, the thing is that iridium is citrophile, so most of that is going to end up in the crust in a differentiated body. In an asteroid, you've still got cosmic abundances. So relative to the crust of the Earth, an undifferentiated asteroid is enriched in iridium, which is why you can tell that, for instance, the Cretaceous Tertiary impactor, was an asteroid or a comet, because it was much richer in iridium than the crust.
Yeah, I see. But then again, what we know for what the asteroid has is only because what we are able to get for the spectroscopy reflection of the light. So probably we will only have that iridium or whatever in the surface of the asteroid, not inside. Well,
actually, no. We actually have a lot of samples of asteroids in the form of meteorites.
Yeah.
So we have about, for the most abundant meteorites, we have about 90,000 samples. For things like iron asteroids, we have about 1,200 samples.
But what I always think, I'm sorry, Dan, because probably it's ignorance, and I just want to be clear about this. I always think that when we have, regarding to meteorites, is something that have crossed our atmosphere. So anything which was not metal has been vaporized. So what we have here is not the same that should be out there. Probably that's my point.
Well, that's true. So what you're going to do is get a bias to the strongest materials.
Yeah.
So the collection is biased to things called ordinary chondrites because they're very strong.
Yeah.
And for iron meteorites, which are also very strong. But we do have a fair number of carbonaceous meteorites.
Yeah.
And volatile-rich carbonaceous meteorites, some of which are very, very weak. And those things are very close to cosmic abundances.
Uh-huh.
And something like Orgueil, which fell in France back in the 1800s, is almost exactly what you'd expect for cosmic abundances.
So you are able to infer that probably what is out there is closely related to what the cosmic enrichment. Okay, I get it. So another question, that's one from me because nobody else is raising his hand. Please, everybody, feel free to do so. Don't be afraid. Even if someone feels not confident with his English, we can try to translate. You can see how freely I talk, and my English is horrible, and my accent is even worse. So don't be afraid. Don't be afraid. So my question is, going back to the permanent settlement on the moon. I know that there are some initiatives regarding because everybody is more or less thinking in build structures and maybe cover them with regoliths or something like that. But I am wonder how possible it could be to go meaning for someone is someone has his Maria Jose. Yes, now he has been able to work. So what I was thinking is what will be if it will be eventually possible to meaning and do an underground under moon permanent settlement, even knowing that the terrain is not consistent, at least at the beginning. What is your opinion about that? Because not many people think about that possibility. Everybody more or less thinking building surface structures or things like that. What do you think about that?
I think that's probably a great idea. People have been talking about using lava tubes, which are characteristics of the Mare areas, and some of these lava tubes on the moon are very massive. And the nice part is that it gets you out of the radiation environment that
exactly
is a very big problem on the lunar surface.
And what do you think about micro impacts? Because we will not have atmosphere there to protect us from the meteorites or things like that.
whatever you wear out on the surface needs to be strong enough to survive a micrometeorite moving at cosmic speeds, 20 or 30 kilometers a second. And even a piece of dust has the kinetic energy of a pistol bullet at that rate of speed.
Exactly my point. Even Phil was talking about landing pads and the problem to get the small pieces of regolith moving and eventually hitting something. If we get a permanent settlement under the surface, we will not need to worry about that, or at least not in the same way. So you think it's a good idea then?
I think it's a great idea. And Phil pointed out, I think, a very useful issue is that landing and takeoff operations are going to produce high velocity ejecta from the plumes, and people who have surface facilities are going to have to think about how to protect themselves.
Yeah.
Or we'll have to think about how to mitigate this high velocity ejecta, landing pads, berms, things like that. Because we're not going to be, NASA is not the only user of the moon. And I doubt if future ESA or JAXA or Chinese expeditions would appreciate being sandblasted by each other's plume ejecta.
Most certainly not. No, of course not. So there is another advantage, I think, I want to discuss with you. Probably you can have a big infrastructure and you only need to worry about lock it, to maintain a contained oxygen-rich atmosphere in a big place with a single door, let's say. If you have many different settlements, you need to worry about to have an atmosphere contained enough to living things in each of them.
Yes.
And with a single door here, provided that you are able to do, you can do it as big as you want. You can. So I can see a lot of advantage, and I was planning to propose to my regional government to present a proposal asking for funding to experiment in the different techniques to survive in a potential underground settlement under the moon. And now I can tell that Daniel Britt thinks it's a good idea. So it's a good thing that you also think is a good idea.
I'm not the only one.
You are not the only one.
There's a lot of interest in that.
Okay, thank you very much for your presentation again. It has been fantastic. If everybody here, we have another hand raised. Let me. It's Isidro. Please, yes, Isidro, go forward.
Actually, this is a question in the chat from Susana.
Okay.
She thanks you for the nice presentation, Daniel, and she asks if there are lithium enrichment. If there is lithium enrichment in the moon regolith.
Say again?
If there is lithium enrichment in moon regolith.
Probably it would. That is a question I don't know. I will guarantee you that there's very little enrichment in the highlands terrain. But I would have to look into the creep and see how much lithium is in the creep.
And you are interested in lithium for something, Susana? Because Susana is also a geologist, and she also is beginning to work with planetary geology. I was wondering why Susana wants to know that. Susana is a colleague of our institute, by the way. But it seems that he has not microphone.
Well, lithium is a strong lithophile, so it certainly could be enriched in the lunar crust or in the lunar mare.
Okay, that's really nice to know. And I don't know, anyone else want to ask for something? We have a wonderful opportunity here. Have a real expert, a real nice person willing to answer our questions, our silly question in my case. So please take advantage. No? Okay. So, Dan, has been a real pleasure to have you here. You know where your second home, your second Oviedo home is. Whenever you want to come to Spain.
Okay, I'll keep that in mind.
Keep that in mind, of course. Please send my regards to Mark whenever you have the opportunity to see him, Mark Dewey. Tell him that we still remember him here. Nice. And well, whatever you need from us, we are here to help. And maybe we will send you in the next few days one email with a few questions from the people who is shy and not.
Certainly.
Okay,
yeah, if anyone has questions or wants to continue discussions, you have my email, so please feel free.
Thank you very much for your willingness, and don't know what to say, except that we are going now to clap virtually if we are able to. Yes, I say wonderful. Maybe you can see in your screens like the clapping is happening.
Oh, thank you.
No, of course. Thank you for giving us some of your time. And looking forward to meet you in person and to meet you again and to have the opportunity to invite you here. Dan, has been a real pleasure.
All right. Well, thank you very much. I enjoyed it.
Yeah, thank you.
And have a great evening.
Exactly for you. Yeah, have a good morning or whatever, and the rest of the day for you.
All right.
Okay.
Bye now.
Bye. Bye, everybody. Bye.